Now we are doing derivation of MCR regarding the beam. Let's continue. In the last lecture, we introduced this local coordinate. So from now on, I'll calculate the external moment regarding local coordinate. It is 3D plane. We have to consider the 2D plane in order to understand easily. Let's calculate the local the moment due to this the external global the moment. Let's look at the 2D plane. So we consider XY plane, XZ plane, YZ plane like that. Firstly, let's look at the XY plane. Then this is X, this is Y. Then you have the local coordinate the angle lambda, gamma like that. That is local Y prime. You have a little downward downward x prime. Here you have the moment, right? Against the x-axis. If you draw the moment like that, this is the end moment. If you consider this free body diagram, the moment must be applied this direction due to equilibrium, due to satisfy equilibrium. So you draw this x direction. This moment can be divided into mz prime external prime, that is local coordinate, and then this y. Let's calculate the moment of local coordinate from the moment of global coordinate. Mx prime external is equal to mx external times cosine gamma, right? Gamma is the small angle, so you can write mx external like that. Okay, let's look at y prime external in this direction. You have this one, right? So that is opposite direction. So you have a minus here. So mx external times sine relationship, right? Sine gamma equal minus mi external. So small diffraction theory, sine gamma equal gamma. That is xy plane. We calculate the local coordinate, the moment through this the plane analysis. Let's look at the other plane. YZ plane. YZ plane is, this is Y, this is Z. Regarding global coordinate X, Y, X. This is Y, Z. And then you have a little downward Z prime here. So downward Z prime. So the angle here is dV over dz, that is v prime. Let's draw the moment, external moment here. Do you have my external or mz external? No, you don't have. So the local, the moment mi prime external, mz prime external must be 0 in this yz plane analysis. How about xz plane? Xz plane is xz. xz. It is plan view, right? Plan view. So xz. If you see the plan view, so z prime direction like that, x prime direction like that. So this angle must be, this displacement is u because it is z direction, u. du over dz, that is angle u prime. You have axis moment. Do you remember? This moment corresponding to this x-axis. So you can draw x-axis moment can be divided into two, mx prime and z prime. From this plane, you can calculate mx prime external equal mx external times cosine this angle. This angle is equal to u prime du dz. So the small angle, so it is equal to 0. So mx external. How about the mz external? Mz external is mx external sine relationship. Okay, sine du dz. Sine du dz is u prime. Mx external u prime. The reason we divide into these three planes is that it is somewhat complicated to calculate this local coordinate moment just using 3D plane. So we introduce this 2D plane. If you summary these three, the plane analysis, mx prime external equal, you see, mx external. What is mx external? Equal m0, right? So how about my prime external? You don't have here. This is 0. If you see this angle, xy plane, and y external equal minus mx external gamma. So that is minus m0 gamma. How about mz external, mx external, u prime. This is external moment of local coordinate. So we have to calculate internal moment of local coordinate. So if you calculate internal moment also, then you can establish the equation. External moment is equal to internal moment. That is a procedure. So let's look at the internal moment corresponding to this local coordinate. So x, y, z, local coordinate. You have the displacement of v. That is the moment like that. Mx prime internal. Prime internal moment equal to minus ei v 2 prime. It is very famous equation, right? Yeah, well-known equation. It is originally EIX prime V2 prime. IX prime is almost equal to IX. So minus EI IX V2 prime. We can write. Also, let's look at the MY internal. So let's look at X prime, Z prime, Y prime. That is regarding MY prime moment. MY prime. This direction. So here y prime is, if you see the compared to this one, is opposite direction. So minus should be minus mi prime internal is equal to I e y u2 prime. So from this one you can get y prime internal equal e I y u2 prime. Right? How about mz prime? Mz internal moment. And we already calculate the Saint Venant torsion, warping torsion. Okay, that is the equation regarding torsional moment. That moment regarding Z prime is torsional moment. So mz prime internal equal gj gamma prime ecw gamma 3 prime. In this derivation, we assume rectangular bar. So rectangular bar is the simplest case. We consider rectangular bar firstly. So in rectangular bar, warping constant is equal to 0 because there is no fringe, okay, in rectangular bar. So this mz internal is equal to gj gamma prime. We only have Saint Venant torsion. So it is the derivation regarding internal moment. Mx prime internal is this one, mi prime, this one, mz prime, this one. Nextly, we can establish equilibrium of internal and external moment. These are external moment regarding x direction, y direction, z direction. So external moment m0 equal to internal minus EIX v2 prime. External moment regarding y, internal moment regarding y. External moment regarding z, internal moment regarding g-axis. That is the equilibrium equation. If you move this one on the left hand side, then you can get equation number 1 arranged, then you can get this equation. From this one you can get this equation. If you investigate this equation, v prime is a vertical direction, right? V is a vertical displacement. This equation is in plane bending, low deflection problem. You must be very familiar with this equation. EI v2 prime equal m0, right? M0 equal minus EI v2 prime. You must be very familiar with this equation. I mean, form is very familiar. In the case of column buckling, EI y2 prime equal plus P equal 0, right? This is beam. So instead of P, you use m0 here. So in plane bending problem. This equation 2, equation 3, you see here u2 prime gamma here. Here gamma prime u prime. At the beginning of the beam, I mentioned u and gamma, they are coupled. As you see, they are related each other. Gamma prime, u prime. So this u is a lateral displacement, gamma is torsional angle. So these two equations represent lateral torsional buckling. If we draw some curve, in this problem, if moment increase, then vertical displacement increase because it's a low deflection problem. This lateral torsional buckling, ultimately, if the moment increase a little bit, there is no deformation regarding u and gamma. It reached to MCR. Okay, MCR, critical moment, critical buckling moment. Then it suddenly buckle, and then it has sudden displacement U and gamma. That is eigenvalue problem or bifurcation problem. Yeah, if we consider the column, this beam behavior simulate the column, except its complexity, because it is a 3D problem. Okay, we are now calculating MCR, so we are interested in these two equations, equation 2 and 3, solve that MCR. So firstly, we take derivative of equation 3, then Gj gamma 2 prime minus M0 U2 prime equal to 0. It is equation 4. So if you input this equation into 4, then you have Gj gamma 2 prime M0. What is U2 prime? From this equation, U2 prime equal minus M0 gamma divided by EIY, like that. So finally you get this equation. And then if you rearrange this equation, gamma 2 prime plus M0 here square, and then divided by Gj here. So EIY Gj gamma equal to 0. Less K square equal this one, M0 square EIY Gj. Do you remember in column case? We read K square equal P over EI, right? We have some similarity between two, column and beam. So gamma 2 prime plus K square gamma equal 0. It is a second order differential equation. What is the solution? Gamma equal A sine kz plus B cosine kz. That is homogeneous solution as well as general solution. You have two unknown A and B. You have boundary condition, right? At the beginning, at both ends of this beam, we don't have any rotation at both ends, right? That means gamma is equal to 0. So gamma 0 equal to, this is 0, B. Okay, equal 0. Gamma L A sine KL equal to 0, right? Yeah, it is very similar to the column case, right? And then sine KL equal to 0. That means KL equal to n pi in order to satisfy this equation. So from this equation, what is your K? K is this one. If you input this one into here, that means M0 over square root EI Gj. Then you can finally get M0 equal n pi L root EI Y Gj. So critical moment is called MOCR equal n equal 1, the minimum value of this one. That case is n equal 1. So pi over L, the square root EIY Gj. That is critical moment regarding simply supported beam. Both ends are restrained against the rotation. That case. Then let's look at that MOCR for wide frame section, this section. Before we just consider rectangular section. How about the wide frame section? So MZ internal equal GJ d gamma dz minus ECW d cube gamma dz cube, like that. So we have this whopping resistance term regarding internal moment. Wide frame section, we have whopping resistance. Rectangular section, we have this term and this term. But in the wide frame section, we have this term, additional term like that. This again the differential equation, fourth order. If we solve this one, detailed procedure, you can see the textbook because it is limited time. If it's the result, MOCR equal pi over L root 2 EIY Gj. It is identical to rectangular section. This wider frame section, we have the additional term here. Square root 1 plus W square. W means this one. That is the result for wider frame section. How about different end moment cases? Up to now, we assuming the same magnitude of moment at both ends, right? In that case, if it is a wide frame section, MOCR equal can be written like this. In that case, we have the uniform moment like that. This is the most critical case. If we have different moment, let's say here M0, here 0.5 M0, in that case, the beam strength regarding lateral torsional buckling increase. Okay, torsional buckling strength increase if the moment magnitude are different. We already studied a very similar thing in that column, right? So in the case, if the moment is different, then MCR equal MOCR times CB. So the MCR increase by CB times. Okay, so CB can be calculated 1.75 plus 1.05 MAMB plus 0.3 MAMB square. That must be less than 2.3. This equation comes from some researches. Let's look at this case. MAMB. So the magnitude of the moment and both ends are different, MA and B. It makes still the single curvature, right? It deflects like that. It called the single curvature. So in single curvature case, MA over MB equal minus, we use minus. If MA over MB equal minus 1 over 2, if we input these things, CB value is 1.3. So lateral torsional buckling strength is increasing 1.3 times compared to same end moment cases. That means every section and yield strength is identical, only moment distribution is different. The lateral torsional buckling strength is different. How about the double curvature case? MA over MB is equal to plus double curvature. Double curvature means this will deflect, deform, and like that. This case, down, up. That is double curvature. If MA, MB, the ratio is equal to 1 over 2, then CB equal 2.35. Okay, it must be less than 2.3. So the critical moment in this case is 0.3 times bigger than the equal the moment cases. Let's see in next week.